Okay, so let's say we have a sphere made of some sort of reflective material and we've marked the center, but we don't really need the entire sphere. Let's say we just have a portion of a sphere, but we still care about where the center of that sphere is. And let's say we've got a ray of light coming in from the left. Let's say a horizontal ray of light coming in like this. We know that's going to reflect off of the surface, but how do we typically decide which direction it's going to reflect? Or what angle would we actually measure there? Generally, whenever we're talking about reflection or refraction, like a ray of light hitting a surface and either going through or bouncing off, any angles we're going to care about, we're going to be measuring from the normal line. Normal line in the sense of a line that is perpendicular to the surface itself. And for a spherical surface, it's really easy to draw in a normal line because any line that's perpendicular to the surface is going to have to go through the center of the sphere. So to draw a normal line to a surface of a sphere or circle, you can just draw a line from the center of that sphere or circle towards that point on the surface and keep going. That's going to be a line guaranteed perpendicular to the sphere itself or the circle. And in terms of direction, we can say that the incoming ray of light makes this angle, let's say theta, with the normal line. So that angle theta is the angle between the incoming ray of light, the incident ray, and the normal line. And the ray of light is going to bounce off. So it comes in, it hits the surface, it bounces off. And what can we say about the angle that the reflected ray makes with the normal line? This angle right here. Yeah, it should be identical. This is usually referred to as the law of reflection or the principle of reflection, that the angle that the reflected ray makes with the normal line is going to be exactly the same as the angle that the incoming incident ray already made with the normal line. So these two angles are congruent to each other. So that's very predictable in that sense, that we can expect that the reflected ray makes the exact same angle with the normal line that the incoming incident ray did. And that's going to be true for any ray of light we care to draw. That if we draw in, let's say, a ray of light down here, and for this ray of light, we could draw in the normal line at that point. Normal line, again, being a line perpendicular to the surface, which for a spherical mirror is guaranteed to be a line through the center of the sphere. So there's our normal line. And the reflected ray is going to make the same angle with the normal line. So these two angles have to match. And we could do more rays as well. We could draw in, let's say, actually, what if we draw in one that's coming in along the optical axis here, along a horizontal straight towards the center? How is that going to reflect? If it's coming in along a normal line already.
It's coming out the same way it's going in.
Sorry, what was that?
It's reflect the same way as it's going in.
Yeah, that's going to just reflect exactly the same path it came in along. Because what angle is it making with the normal line right now on the way in?
Perpendicular.
It's perpendicular to the surface. So what's the angle it's making with the normal line itself?
0.
Right. It's making a 0 degree angle with the normal line on the way in. So it's going to also make a 0 degree angle with the normal line on the way back out. It just bounces straight back along the line it came. And if we draw in some other ones, like let's say we draw in one that's close to the obstacle axis. We draw in that normal line. Notice that this incoming ray of light makes a fairly small angle with the normal line. So it's going to bounce back, making that same small angle with the normal line. Something like that. And then we could draw in as many more of these as we want to get a more accurate idea of what's going on. Again, drawing in the incoming ray of light, drawing in a normal line at that point on the surface, and then drawing in the outgoing ray of light after it bounces off, making the same angle. And what we really most care about here, if you just look at the outgoing rays of light, so ignoring the incoming rays of light, just looking at those outgoing rays. Are those outgoing rays ever going to intersect on that side?
No.
No, they're not going to intersect. But since they're not parallel, they all seem to have come from some other point further back. If we backtrace these, we can say this ray of light seems to have come from back here. This ray of light seems to have come from somewhere back here. This ray of light from somewhere back here. And likewise, this one and this one. This one a little bit off. But if I've drawn this right, it seems like all these rays of light seem to have come from a single point. Even though they never actually passed through that point, we can say the final rays geometrically all seem to have come from this point. And this is really the main important property of a mirror like this. If you've got a convex mirror, a mirror that sort of bulges out towards the source of the light, those incoming rays of light were originally parallel, but even though they started off parallel, they all bounce off, spreading out from each other. But they all those final rays of light that were originally parallel, all seem to be coming from this one point. And that one point we call the focal point or focus of the mirror. So this one point is the focus of the mirror. Any questions on the terminology there so far? So once again, if you've got a convex mirror, a mirror bulging out towards the source of the light, any rays of light that started off parallel to each other bounce off and spread out. They diverge from each other. So we often call this a diverging mirror. And they all specifically seem to be spreading out from one single imaginary point behind the mirror, which we call the focal point. So this convex shaped mirror is diverging. We would call it convex to describe the shape. We call it a diverging mirror to describe what it does to light. Any other questions on that so far? So the most important property of this is that any ray of light that starts parallel, specifically parallel to the optical axis, reflects to become collinear with the focal point. That is, it reflects so that it's now traveling along a straight line that includes the focal point. And this is also reversible. If we have a ray of light that's coming in along a line that goes through the focal point, every path light takes is reversible. So if you have a ray of light that's coming in towards the focal point, if you got a ray of light that starts coming in towards the focal point, even if it never actually gets there, here's a ray of light that starts off along the same line as the focal point. What's going to happen to that ray of light when it hits the mirror? That's going to bounce off to become what?
Will it be linear?
Well, any ray of light is linear, but specifically linear in which direction?
Sorry, parallel.
Yeah,
Like,
parallel to that central axis again.
yeah.
And this is what I mean by reversible. And any path light can travel can be traveled in either direction. So a ray of light that starts off parallel bounces off to become collinear with the focal point. But also in a reverse, any ray of light that starts off collinear with the focal point is going to bounce off to become parallel. So this is true in both directions. Any ray of light that starts collinear with the focal point is going to bounce off or reflect to become a parallel to the optical axis. Parallel to the optical axis. So those are two of what we call the principal rays. And of course, there's many rays of light that could be hitting this mirror, but some of them are very predictable, very comparatively easy to draw out because of their relation with the focal point and the parallel to the optical axis. So we call these the principal rays in the sense that they are the ones that we should be drawing out first. Also, one other ray, or a couple of other rays, I guess, that are comparatively easy to draw. One of them is if you've got a ray of light that happens to be traveling straight towards the center of the sphere, that is collinear with the center of the sphere itself. Let's say you've got a ray of light that comes in along that line. And of course, it's not actually going to hit the center because it's going to hit the mirror first. But how would that ray of light reflect? What's going to happen to that ray of light if it's originally coming in along the normal line?
Is it gonna come back like the same exact angle back? So like on top of each other?
Yeah, exactly. Because it came in making a 0-degree angle with the normal line. So it's going to leave also making a 0-degree angle with the normal line. So this is another ray we can often draw in very predictably. Any ray towards the center of the sphere is going to reflect back along the same path. No bending at all. No difference in path. It just bounces off exactly the opposite direction. So these are what we often call the three principal rays. If you're talking about a certain location where light is coming from, drawing out these three rays is going to make things a lot easier. Also, one other thing about the focus, where is the focus located relative to the sphere itself?
It's located.
Is usually, you can go.
Sorry, located where?
I was gonna say it was located R/2.
Yeah, half the radius, exactly halfway between the center and the surface. And I think I've drawn it a little bit, not quite to scale here, but formally the focal point should be exactly halfway between the center of the sphere and the surface of the sphere. So half the radius away from the center and also half the radius away from the surface itself. And generally, we're going to be measuring any and all distances from the surface of the sphere. So let's try actually applying this to finding an image from an object. The idea of an object is if you just got some thing over here that's emitting light. Like let's say we just got some object here, some physical thing that's emitting light. And maybe it's like a candle or a light bulb or something that actually is producing light. Or maybe it's not producing light, it's just reflecting light from the sun or from a light bulb or something. But either way, whether this is actually producing light or just reflecting light from somewhere else, we can treat this location as where the light is coming from. And let's say we focus on just the top of the object. So we've got rays of light coming from the top of the object, Anything in between is going to follow suit. But let's say we've got rays of light from the top of the object coming out in all possible directions. So rays of light from the top of the object coming out in many directions. But we don't really need to look at every possible direction. We only need to look at the principal rays because those are going to be the most predictable to draw. And then everything else should follow the same pattern. So let's try these three principal rays. A ray of light that starts parallel and reflects to become collinear with the focal point. So from the object, specifically the top of the object, we could draw a ray of light from the object that starts parallel to the optical axis. It's going to hit the mirror and reflect off in what sort of predictable way? If it starts parallel, then it's going to reflect to become what?
It's going to go through the focus.
Yeah, or become collinear with the focal point. It won't actually pass through the focus because this ray of light isn't going through the mirror, it's bouncing off the mirror. But it's going to bounce off the mirror in a way that becomes collinear with the focal point. So I'm going to draw in this line through the focal point and the point where the ray of light hits the surface. This extra line isn't really part of the diagram. It's just to establish sort of a framework. The important thing is the incoming ray of light that started off parallel hits the mirror and bounces off along a line through the focal point. Or you could also describe that as it reflects directly away from the focal point. But the important thing is the new ray of light after the reflection is collinear with the focal point. So that's one of the principal rays we can draw. A ray of light from the object that starts off parallel to the optical axis and bounces off to become collinear with the focal point. Another one we can draw in is a ray of light that starts off collinear with the focal point. That is, it starts off going straight towards the focal point. But of course, it's not actually going to get there because what does it hit first?
The mirror.
Yeah. So if you got a ray of light from the object towards the focal point, but then hitting the mirror, that's originally collinear with the focal point. So it's going to bounce off to become what?
Parallel.
Yeah. If the ray of light starts off collinear with the focal point, then it bounces off to become parallel to the optical axis. And these two alone would be enough. We could use these two rays to find a point of intersection where they seem to have been coming from. So two rays are enough to settle the result. But it's a good idea to draw in the third ray as well, just to be absolutely sure. Make sure they all intersect at the same point. Specifically for the third ray, if we've got a ray that's towards the center of the sphere, not the focal point, but the center. But of course, that's also never going to get there. It's going to hit the mirror first. So a ray from the object towards the center of the sphere is going to hit the surface and bounce off in what sort of way?
Directly back the way it came.
Yeah, straight back exactly the way it came from. So those are the three final results of the principal rays. And again, there are many rays of light produced by this object. These are just the three that are most straightforward to draw. So these three principal rays, they started off spreading out from the object, they hit the mirror, and now they're diverging even more. They're spreading out even further than they were before, which is why we call this a diverging mirror. And since they're diverging, these rays are never going to hit on the left side. But if we backtrace, we can find a point where they seem to have come from. That is, this ray of light seems to have come from back here. This ray of light seems to have come from back here. This ray of light seems to have come from back here. And note that we can find one point. Let me actually shrink the focal point a little bit so we can get a better look here. Because this is not the focal point. But there is one location where these back traces intersect. That's one location that all three of these final rays of light seem to have come from. So I'm going to put a mark there, because if you're standing over here and you see these three final rays of light hitting your eyes, your brain is going to assume, the object must have come from somewhere back there. So if your brain sees just these three rays of light, let's say you don't see the object itself. If all your eyes see is these final three rays of light, your brain is going to think, oh, those rays of light must have come from this point back here. Did the rays of light actually come from that point? Where did these rays of light actually originate?
From the object?
Yeah, the rays of light originally came from the object. But as far as the parts of your brain that deal with vision are concerned, these final three rays of light seem to have come from this empty point over here. So that point that the rays of light seem to have come from, we call that the image. So the object is the actual physical thing that the rays of light really came from. The image is the location where the final rays of light seem to have all come from, the intersection of those back traces. Did the rays of light even pass through that point, though?
No.
Like these orange lines I just drew in, that wasn't the actual path light took. All the light is on the left side of the mirror here. These orange lines were just back traces, hypothetical, well, the light ray of light could have come from here, even though it didn't. So since we had to backtrace, the rays of light never really passed through this point. So we would call this a virtual image. Image meaning the rays of light seem to have come from that point, as far as anybody looking at the final rays of light is concerned. But it's called a virtual image because the rays of light didn't actually pass through that point at all. Any questions on the terminology there so far, or how to find where the image is?
No.
So if you're standing over here, let's say you can't see the object right now, it's covered up by something. But if you look in this spherical mirror, you're going to see what looks like a second copy of the object, which is really just the image. And how does that image compare to the object itself?
Smaller.
It's definitely smaller. Yeah, you're going to see this miniaturized copy of the object that seems to be inside or beyond that mirror surface. And also note that it's closer to the mirror surface than the object itself was. In fact, we can draw out a triangle here that might be useful to consider. If we draw a triangle with the object height as one of the sides, and the distance to the mirror as one of the sides, and then a hypotenuse, we could also draw a triangle with distance to the image as one of the sides, height of the image is another side, and this hypotenuse. What do you think we can assume about those two triangles geometrically?
They're proportional to each other.
Yeah, these are similar triangles, so they're going to be proportional to each other. And that means we can set up a ratio of sides. Specifically, the ratio of height to height, image height over object height, image height over object height is going to equal the ratio of image distance over object distance. That is the horizontal distance as measured from the mirror outwards. So image distance over object distance is going to be the same ratio. Image height over object height, the apparent height of the image divided by the actual height of the object, is going to match the ratio of the distance from the mirror to the image over the distance from the mirror to the object. And this ratio, image height over object height, is usually called the magnification factor. In the sense that the image height over object height ratio tells you how magnified the image appears to be. Like if the magnification factor is exactly, let's say 1/3, that means the image height is 1/3 as much as the object height. Or if the magnification factor is 20, that means the image seems to be 20 times as bigger than the object. So the magnification factor, if it's more than 1, that means the image is bigger than the object. If smaller than 1, that means the image is smaller than the object. And that will always match the ratio of the image distance versus the object distance as measured from the surface of the mirror, because of these similar triangles here. Any other questions on that ray tracing or the terminology of objects and images so far? Then let's try out a different approach. Let's say instead of sending in light on the convex side, let's send in light from the concave side as well. Sending in light from the right side here. Let me tighten this up a little bit. And let's say we put the object on the right side of the mirror. Somewhere like here. In that case, we're going to have to rethink our principal rays. For example, if you send in a ray of light coming in like this, how is that going to reflect? If it starts off parallel to the axis and hits this concave side, what would you expect to happen?
Would it go through the focus point?
Yeah, it's still going to bounce off through the focal point. So any ray of light that starts off parallel is still going to pass through the focal point. And the focal point in this case will still be halfway between the center of the sphere and the surface. But notice what happens if we send in lots of rays of light parallel. If a ray of light starts parallel, that's not quite parallel. If it starts parallel to the optical axis, it's going to bounce off through the focal point. If this one starts parallel, it's going to bounce off through the focal point. This one starts off parallel, it's going to bounce off through the focal point. In this case, these rays of light started off parallel, but instead of bouncing off and spreading out, they bounce off and converge towards each other. They all converge to intersect at the focal point. So we call this a converging mirror. It's concave in shape, but the behavior is converging. So a mirror can be described in two different ways. You can describe it in terms of its shape, convex versus concave, or you can describe it in terms of what it does to the light, diverging mirror versus converging mirror. And generally, a convex shaped mirror will cause light to diverge. A concave shaped mirror will cause light to converge. Any questions on that so far? And again, this is reversible. A ray of light that starts off going through the focal point, or at least collinear with the focal point, is going to hit the mirror and bounce off to become parallel. And likewise, we still have the property with the center. Any ray of light through the center or collinear with the center is going to hit the mirror and bounce off exactly along the way it came. So let's try some ray tracing with the object again. We've got an object. If we start drawing in the three principal rays, we could have one ray of light that starts off parallel to the axis. So from the object, parallel to the optical axis, is going to hit the mirror and bounce off through the center. And keep going, or through these focal point and keep going. So a ray of light that starts off parallel to the axis is going to bounce off through the focal point. Alternatively, from the object, we could have a ray of light that goes through the focal point hits the mirror, and what's that one going to do?
Come off parallel.
Yeah, that's going to bounce off to become parallel to the axis. So something like that. And then we could also draw a third principal ray that starts off from the object collinear with the center of the sphere. And what's going to happen with that one?
You're gonna come straight back the same way it came.
Yeah, straight back the way it came. So those are the three principal rays. And we want to figure out if you're standing over on somewhere on this side of the mirror, where do those three principal rays seem to come from? And I think it might help if we erase the original three rays that were coming from the object. If we just look at the resulting rays. So if you're standing over here and you just see this ray and this ray and this ray, can you identify one point where those three rays seem to have come from? And again, remember the rays originally came from the object, but it looks like, yeah, this point in front of the mirror here, where those pink lines intersect, that's where all three of these rays of light seem to be coming from. So we would call that location the image. And again, the image just means the single point where the final rays all seem to be coming from. If you ignore everything else that's going on here, ignore the actual mirror itself, you can still say these final rays of light seem to be coming from this one point. So that one point is what we would call the image here. Let me put those lines back. But yeah, the final rays of light all seem to come from this point right here. So we would call that the image. And what do you notice about that image as compared to the original object?
It's inverted.
Yeah, it's inverted. It's upside down compared to the original object. Also, what can you say about its size? Yeah, small. Also, although I'd say smaller and upside down, not smaller and right side up. Because this is definitely smaller than the original object. And also it's upside down in the sense that the object was above the axis. This image is below the axis. So it's flipped upside down compared to the original object. It's reflected. And also smaller, this also goes back to the proportionality thing. If you draw out the similar triangles, we've got the triangle for the image and also the triangle for the object. These are going to be similar triangles, so they're really proportional to each other. The image is smaller because it's closer to the mirror than the object is, because that ratio of image height over object height should match the ratio of image distance over object distance, this idea of the magnification factor. And one other bit of terminology here, we call this the image because it's where the final rays of light seem to be coming from. Did the final rays of light actually pass through that point, or did we need to backtrace?
Sorry, can you repeat that question again?
The final rays of light seem to be coming from this point that we're calling the image. Did those final rays of light actually pass through that point, or did we have to backtrace to find that point?
It did.
Yeah, they really did pass through that point. So we call that a real image. Any type of image is just the point that the final rays of light seem to come from. A real image means the rays of light really did pass through that point. Whereas a virtual image means they just seem to have come from that point, but you have to backtrace to find it because they didn't actually pass through that point. And typically the real image is going to be on the side of the mirror that light's actually traveling on. A virtual image would be on the dark side of the mirror where light isn't actually happening. Any questions on that so far?
You said this one is upside down, not right side up, right?
Yeah, the real image here is upside down. And in fact, that will generally be true. A real image is going to be flipped upside down. A virtual image is going to be right side up.
Thank you.
And this also goes into the idea of just the concept of reflection. If you draw any ray of light from the object, let's say towards the center point here, it's going to bounce off like this. So the ray of light started off above the axis and reflected, so it's now below the axis. The only way to get above the axis again is if you backtrace to the other side of the mirror, which would have to become a virtual image. So any real image is going to be inverted compared to the original object. Any virtual image will be the same orientation as the original object in the sense of right side up. Any other questions on the mirrors and the images that result so far? And note that what we did here was we put the object fairly far away from the mirror. You can get some interesting different results though if you put the object close to the mirror. Let's see what that would look like. Let me erase the ray tracings and the image. Let's say we put the object much closer to the mirror, like inside the focal distance. Let me make it a little smaller also. So here's an object that's close to the mirror. If we try drawing the ray tracings here, same idea. We could have one that starts off parallel. Let me make that a little smaller. A ray of light that starts off parallel and bounces off to become collinear with the focal point. We could also have, the thing is, a ray of light from the object through the focal point, that's never actually going to hit the mirror, so that doesn't help. What we would do instead is a ray of light from the object straight away from the focal point, because that still counts as collinear. That's still a ray of light that is along the same line as the focal point. So how is that one going to bounce off? If it starts off along the same collinear line as the focal point, it's going to bounce off to become what?
Parallel?
Yeah. Anything that starts collinear with the focal point will bounce off to become parallel. And likewise, we could have a ray of light, again, not really from the object towards the center of the sphere, because that'll never hit the mirror, but an object or a ray of light from the object directly away from the center of the sphere. That is along the same line as the center of the sphere. So if we have a ray of light that's along this line, collinear with the center of the sphere, so from the object, collinear with the center of the sphere, that should bounce back in what way?
The same way.
Yeah, exactly back along the same path through the center. So the three rays of light from this object end up bouncing off in this sort of fashion. Are these three rays of light going to intersect if we continue them?
No.
No, there's never going to be an intersection in this particular case. So we get no real image on this side. Can we still find an image anyway?
Can we extend the from their tail?
Yeah, we can always extend these rays of light in the other direction. We can extend them, we can backtrace them in the opposite direction. Because again, we're just trying to find, ignoring everything that actually happened, ignoring where these rays of light were from. We just want to say, if you're standing over here and you get these rays of light reaching your eyes, your brain tries to figure out where did those rays of light come from? And as far as you can tell from just these final rays of light, those rays of light seem to have come from some point further back. So as far as the parts of your brain dealing with vision are concerned, these rays of light all seem to have come from some point back here. So that point where the rays of light seem to have come from would be the image. And what kind of image is that?
Virtual.
Yeah, the rays of light didn't actually come from that point. They didn't actually pass through that point. They seem to be coming from that point as far as direction is concerned. But since we had to backtrace to find it, this is a virtual image. And note that it is also right side up and looks like a little bit bigger than the object itself because it's a little bit further. I don't know, kind of hard to tell in this diagram. I might not have drawn this super accurately. But if it's bigger than the object, that should be because it's further from the lens than the object is, or further from the mirror than the object is. Any other questions on that so far?
Can we find the actual ratio of the image and the object?
Yeah, and if you want the exact values, there's an equation that's useful there that's usually called the thin lens equation because it also works for lenses, but it works for mirrors as well. And the idea is that if you consider the object distance to be O and the image distance to be I, both measured from the surface of the mirror, the equation is 1 over O plus 1 over I equals 1 over F. So 1 over the object distance as measured from the mirror surface plus 1 over the image distance as measured from the mirror surface equals 1 over the focal length, again, as measured from the mirror surface. So they add inversely, which means if you know any two of those, you can immediately find the third one. For example, in this case, let's just assign some numbers here. Let's say we call let's say the focal length is, let's say the focal length is 20 centimeters, and the object distance is less than that. Let's say 12 centimeters. If we fill those in, we should be able to solve for F. So 1 over O would be 1 over 20. I'm going to ignore the units here because everything's in centimeters. So 1 over 20 plus 1 over an unknown image distance equals 1 over the focal length, 1 over 20. Right, object should be 12, not 20. So 1 over the object distance plus 1 over the image distance equals 1 over the focal length. How would we start solving that for I?
Can you repeat what is the distance from where to where again?
All these distances are measured from the surface. So O, the object distance, which we're saying is 12 centimeters, would be the distance from the surface of the mirror to the object. So we're saying that distance is 12 centimeters. Then F is the distance from the surface of the mirror to the focal point. So we're saying that's 20 centimeters. And then I would be the distance from the surface of the mirror to the image. So that would be I.
Okay. Thank you.
And let's say the focal length is given as 20 centimeters. That's usually known for a mirror. Or maybe you have enough information to find it. And let's say we also know where we're putting the object. If we fill those in, 12 for the object distance and 20 for the focal length, how would you start solving for the image distance here? How would you start algebraically solving for I?
So you switch the position of 1 over 20 with the 1 over I, and then you solve for one side first.
Well, algebraically, how would you do that? What arithmetic operation would get rid of the plus 1/12? Yeah, we can just subtract 1/12 from both sides. So that gives us 1 over I equals 1/20 minus 1/12. And yeah, we'll then need to take the inverse. But we'll want to simplify the subtraction here first, though, because ideally we want just 1 over I equals a single fraction. So it's easier to invert. How do we combine 1/20 minus 1/12? What would be a common denominator there? What's the smallest number that's a multiple of 20 and a multiple of 12? Yeah, 60 should work because that's 3 times 20 and 5 times 12. So we could say 1 over I equals 1/20 is the same as 3/60. 1/12 is the same as 5/60. So subtract, we get 1 over I equals -2 over 60. Or in other words, -1 over 30. Invert both sides, and what do you get for I? What's the inverse of -1 over 30? Yeah,
30.
-30. So that means the image distance, the distance from the lens, from this mirror surface to the image is -30 centimeters. And the negative there signifies essentially which side of the mirror it's on. The way I usually think of it is the side of the mirror that light is traveling on at the end is the positive side. The opposite side is the negative side. Like in this case, we send in rays of light, it bounces off, the final rays of light are traveling to the right. So we would treat to the right as the positive side. The actual image is on the other side though, so that means the image distance is negative, specifically -30. Any questions on that so far? And then you could use that compared to the object distance to figure out the magnification factor as well. So use those ray tracing ideas to try out some more examples. You can either use some from the FNT or practice quizzes, or you could even just make some up. Just say we've got this mirror, it's got a certain focal distance, we put an object here, where's the image going to be? And try that with both ray tracing, drawing it as accurately as you can, ideally with a ruler or graph paper, and also try the same thing with the thin lens equation and make sure the geometry and the algebra match up with each other. So try out some examples. Let me know if you have any other questions, and I will see you next time.
Can I ask you something before we go?
Yeah, what's up?
What does it mean to have positive I again?
Positive means on the side that light is traveling on, whereas negative means on the dark side of the mirror, the side that the light is not traveling on at the end.
So it says, so I is positive if the image is on the same side of the mirror. What does it mean to be on the same side of the mirror?
I is positive if the image is on the side of the mirror that light is actually traveling on at the end. So whichever direction light is traveling at the end after it interacts with the mirror or lens, that's the positive direction. So if the image is on that side, then it's going to be a positive value for I. But if the image is on the other side that light's not traveling on at the end, then I will be a negative value.
Okay, thank you.
You're welcome. See you next time.